Welcome to this video tutorial. So this is hopefully a short one, and I just wanted to talk briefly about optimization. So again, using Tesla cavity mixel as a reference. One of the powers of or strengths of parametric modeling is that you could plug in any of these variables into some optimizer which is built in CST Studio, and then you specify some objective function or functions, and then you can um, yeah run the optimization problem here. One of the, I wouldn't say drawback, but then some things to notice that the optimizer, I'm going too fast. So to access the optimization tool in CST Studio, you head over to the simulation tab in CST Studio, and then you see right here optimizer. So you have parametric and also non-parametric optimizers, but now we'll be talking about parametric optimizers. So that's the default when you just click on this, but sorry. And then you could see all of your variables here, which you could select, and then you could define the range of values that's the bounds of your variable. So you have this, and then you could change this to 20% and then reset min max, and then it resets this value, leaving the other one. So if you should tick this, then it's now a multivariate optimization problem, and you can click as many as you want, but then we would only would only use one for now, and then you could play around with any of this. So if you should go to the algorithm, then you have several algorithms which are listed here. You have the trust region framework, the mid simplex algorithm. You could read up on all of these if you just click on help here. So a page comes up that explains the different algorithms and where which problems they are best suited for. Now, what you should notice is that when you define the goals, so you could have several goals. So I could go and add a new goal, and then 2D, 3D results. So I think also depending on the problem you're currently studying, you have the different results. Now you could define, okay, no post-processing result is no post-processing result is defined currently in this model. So when you try to add a new optimization goal, they take you are redirected to the template for post-processing. So now I want to look at frequency. So you remember that frequency is in 3D eigen mode result. Then I go to frequency. I'm going to be calculating for just one mode. So I'm going to check. So I want to optimize the fundamental mode of this cavity. It's currently the Tesla cavity, which is 1300 megahertz, but I would say let me optimize it to 1350 megahertz. So I want it to operate at 1350 megahertz fundamental mode frequency, just as a test. So I'll go. Now I have a post-processing result, but then there's no result yet, so I don't think I can evaluate this, but let me see. Yeah, nothing happens. So, but now I can select it as an optimization goal. So you could make it less than equal to, so I want it to be equal to 1350 megahertz. And yeah, so you could have a slew of other objectives here, depending on what you have listed on your post-processing step, and also depending on the problem. So if we are dealing with a frequency domain problem now, I think you would have by default S parameters in this combo box, in this drop-down combo box. So but now we just have frequency, and then I usually select the difference square because in my experience I noticed that when I use the difference square, and also depending on the problem I'm looking at, it doesn't terminate prematurely, also depending on the algorithm. But then I always find that for some algorithms, if I just use difference, then it terminates prematurely. But then when I use frequent difference square, it doesn't terminate prematurely. Why it does that, I have no idea. So now I have an objective goal. So this is a single objective, single variable, because I selected just one variable, single variable optimization problem. But then I could as well define different objectives, and then you would have the summary type of all the objectives. So either you sum all the objectives or the maximum. So for in CST, to the best of my knowledge, you cannot solve a multi-object. I mean, you can solve a multi-objective, multi-variable problem by reducing it to a single objective multi-variable problem. So, and how you reduce the multi objectives is either you take the sum of the goal or you take the max. So it's either the sigma. So done with this from the last video. So it's either you take the sum of all the goals. Let's say goal 1, objective function 1, objective function 2, or you take the max f1, f2. So, but then, but then what you can do is solve the objective, do a multi-objective optimization where typically you would find maybe a Pareto front, which is a family of solutions that minimizes the problem. So to the best of my knowledge, I don't think CST can do that. So if that's what you're looking for, you might need to look at another program. And then also to mention a caveat, and generally I do not use CST for optimization of cavities, and the reason is because to the best of my knowledge, you can't do 2D on CST. If you know that it can do otherwise, please leave it in the comment because I haven't really thought about it so much because I have other programs that I use for my 2D simulation, so I haven't really looked so much into CST as to if one can actually do a 2D simulation of the cavity on CST. So that's what I generally use for my I use other programs for my cavity optimization, but then if you were to do a 3D optimization, especially for me with high order mode couplers, which are really complicated, and then you can't really treat it in 2D, then CST becomes invaluable for such optimizations, at least so far, as I know. So I'm just going to do this, and then my goal is to get the frequency to 1300 megahertz. So I've defined my variables, I've defined my functions, and then and also define my variable bounds. So the next thing is to and then define the solver. I mean, the solver it selects the default solver, and you could also select template-based post-processing. But then yeah, that's for I wouldn't talk about that. So the eigenmode solver, and then I start this. So it gives you the initial goal function, which is the current values you have, your initial values, which is what you have on this column, which is 103.3. Then that's for the REQ, the equator radius, and then the best goal function and also the last goal function. So it gives all of this and then updates this for each iteration. So I'm going to pause this. I don't know how long this would take. Oh, I also did not apply the simplification. Okay. I'm going to stop this. Then, since I'm just looking at one mode, because the settings for this, the frequency range is still too broad, I think I'll just cancel it and show you what I mean. Discard any parameter changes. Yes, also about post-processing. So what I mean is the frequency range is too large. So since I'm looking at just the monopole modes, I'm going to do this 1250 to 1400. Then I'm also going to apply the symmetry conditions that we talked about in the previous video, so that I speed up my computation. So I'm going to apply magnetic, and I think, oh boy, I hope I did not delete it. I can't get it. Now I don't know which other, I can't remember which other symmetry condition I applied for the, I think it was electric, but I'm not sure, so I'll just, or I could apply it and see. I think it was electric. So for the TM010 mode, I think it was electric. What am I doing? It was electric. Let's see. So, as I mentioned in the symmetry plane video, if you haven't seen it, you should go and check it out. You see that applying three boundary conditions reduce the number of tetrahedrons by 8, a factor of 8, so divided by 8. And yes, I think I was correct. It's E. So what you have here is your TM010 mode. Yes, so this is correct. So now, and you see that didn't take any time at all. So I go back to my optimizer and I start it. So Now you see the initial value because I already ran the simulation once. You have the remember this is a difference square, so it's taking the current frequency, which is 1300, and then subtracting 1350 from it and then squaring that difference. So that's basically what it does. And yeah, that's what we have here. And then you see it's already reduced. So the algorithm I'm using is the default, which is the trust region framework. You already see that it has reduced to 4.6, and then that's just going to, it's really fast. And then it has stopped. Now I would apply this, and then I would look at the frequency. It's I think it should be 1349, yeah, 0.84. Now if I'm not satisfied with this, I think I could start this again. I think if I start this again, it tries to reduce it, but then if it doesn't, then I would change to a different optimization algorithm. I think it should be able to go below 0.02. I think it should give me, oh, I just remembered something. If it doesn't, then I have to change one setting. Yeah, it increased it, but then might still not be sufficient. I might need um a tolerance less than this value. So this is about 1e to minus 4. And if I want to yeah, get a less tolerance, then I can go to properties and then set the domain accuracy. I think this is what I need to change. Let me see, 1e to minus 6, just testing. 1e to minus 6, yes, I think this is what I need to change. Let's see if that works. Yeah, because each of the algorithms, they have their different settings attached to it, and then you can read about how to tweak the different settings to your own, depending on your optimization problem. Yeah, it's you see currently it's 2e to minus 6, but then 2.7e to minus 6, but then the tolerance I put was 1e to minus 6, so it's still running. It hasn't terminated, and then yeah, it would run. So this is the best so far. And yeah, you see the problem is pretty, it's kind of oscillating. Now you could also monitor this by going to 1D results, optimizer, and then going to goals, and then you see how the goals change. So I could view this in log. You see the how the goal changes. Now it wasn't able to reduce it below this because it has, I don't know now, I don't know the termination criteria that is inbuilt into this into the algorithms, but then you see it's better at least than the last one we got to minus 6, but then it's still not below what I set. So you could, I mean, you could try a different algorithm, and then but then I wouldn't go into that, but then they're just different algorithms that you could play around with. And so apply this, and then okay, so you could actually monitor the progress in real time. You see the solution is kind of oscillating. As trust region, if it were a gradient based method, then I think it would just go down. And then you can also look at the changes in the parameter, and then the scale change in case you are looking, in case you're, if you're working with several parameters, then it's usually more beneficial to see the scale change, because if you look at the absolute change, then you have different values and different orders. So it's you would have to look at this scale change. So that's it. And then the algorithm statistics, you could also look at this, and yeah, so the goal sensitivities and everything. So that was it for this video. If you have questions, leave them in the comment section. If you noticed anything wrong, or you have more information that could help others, just leave them in the comment section. If it's really helpful, then I would pin it. Now I don't know if I can move comments to the top or something in terms of, in order of relevance, but then yeah, any suggestion at all would be, or any tips would be, yeah, welcome in the comment section. And yeah, thanks, and see you next video or not.